Welcome everyone to our session today on GraphQL field discovery and query generation using generative AI. So we've got a good, interesting 30 minutes planned here. Our hope is that at the end of this 30 minutes, everyone in this room has a basic understanding of how generative AI applications work, and then also an understanding of how we are using generative AI to enhance developer productivity at Intuit. So let's just start with some introductions.
Yeah, hi. Good morning, everyone. This is Siva, Thiru. I am currently working as a staff software developer at Intuit, and I have been working in the applied AI space and been working building generative AI tools to help improve the productivity of the API developers. Excited to talk about the capabilities that we built at Intuit and also our learning on the Gen AI space.
Hello, everyone. My name is Rachit Sengupta. I am also a staff software engineer at Intuit. As Siva said, we work on an applied AI team at Intuit. Our team is chartered with basically collecting and curating Intuit's internal knowledge, and then building applications on top of that that enhance developer productivity. And so one of the internal knowledges that we have access to is GraphQL schema, and today we're going to talk about how we are using that knowledge to enhance developer productivity in that domain. So the agenda for today is that we'll start by talking about the customer problem that we set out to solve. We will also, at this point, talk about what were the technical challenges that we were solving. We will then go over some Gen AI fundamentals so that everyone on this room is on the same technical level once we go on to talking about our use case and our solution that we've deployed. We will then go into talking about metrics and what impact our solution has had within Intuit. And then we'll talk about some what's next kind of things on what we are doing to improve this entire solution. And finally, we'll round it off with some Q&A. OK, let's talk customer problem. So developers at Intuit really struggle to discover and integrate data to personalize applications. The reason for this is that Intuit has an extremely large GraphQL schema. We're talking millions of lines of code, lots of attributes, tens of thousands of attributes, right? It's so large that not only do engineers struggle to figure out which attributes they need for their use case, but we can't even give the entire schema to like an LLM model. It does not fit in the context window of most models. So we need to figure out a more efficient way to process this data and make it usable for different AIs. So today, to solve this problem, what engineers need to do is they have to use multiple tools. They have to look over documentation on GitHub, developer docs, Google Docs. They have to look at GraphQL Explorer. They have to have lots of meetings with people. And the normal workflow is that they start by first getting some requirements from their PMs. So it could be something like they need a user's invoice volume. They need subscription status, those kind of requirements. And then they try to figure out which attributes can give them this data. And so that's where they have to spend a lot of time on Slack threads, reading through documentation, using these tools. And once they have the correct attributes, then they have to go and write the code and then actually implement it in their code base. What we found is that the middle box, where they're actually trying to find the attributes, that's where they spend a lot of time. And this entire process takes them about 2 to 3 weeks. So to recap, Intuit has a really large schema. People struggle to figure out their attributes. They're spending 2 to 3 weeks. It's so large that we cannot give the schema just to a model. The schema also has issues. There's a lot of collisions, a lot of overlaps. So even if you somehow manage to give it to LLM or some kind of AI model, it might not be able to be the best judge of what should be the attribute the user is looking for. And so that is what we have set out to solve. Those are the technical challenges at hand. OK, so before we proceed to the solution, let's talk Gen AI fundamentals. I want to make sure everyone here is on the same level. OK, so Gen AI is really large language models, is what we're talking about here. And these large language models have been trained at a certain point of time. And so they are aware of knowledge till that cutoff date. So these large language models, in a sense, are a snapshot of knowledge in time. And so what we need is a way to ground these LLMs with relevant information, right? Because our schemas are constantly being updated, new attributes are being added. We need a way to ground it at every time a request comes on what is the most relevant data. Similarly, we have a really large schema, so we need to ground it on what are the correct attributes to look at in this large schema. And so that entire process is called retrieval augmented generation, or RAG. So how does that exactly work? So you start with some kind of domain knowledge. You put that domain knowledge through an embedding model, and this embedding model basically creates a mathematical representation of the data. That mathematical representation is stored into a vector database from where it can be retrieved, and it serves as our context. So when a developer query comes, so a user could come and say, I want the attribute for a user's address. We take that user query, we look it up in our vector database to find the most relevant context. We combine the relevant context with the user query, give it to the LLM, and give the LLM some instructions on what it should do with that information, and the LLM provides an output to us. This entire flow is basically the RAG flow, or the retrieval augmented generation flow. So let's take a deeper dive into this portion of it, right? How does this domain knowledge get converted into relevant context? How does that entire process work? So let's start with some words. So our domain knowledge for this example is going to be just some random words, and we're going to start first with the word orange. So we'll take the word orange and we'll pass it through an embedding model. The embedding model will create an array of numbers. This array of numbers are capturing some information about this word. It's basically gone through a neural network, and the neural network is trained to capture information about this word in numbers. And then these numbers are stored in our vector database. Usually these embeddings that are created are anywhere from a few hundred to a few thousand numbers long. For the purpose of today, and so that we can simplify our visualization, let's pick only 2 numbers from these hundreds of numbers. And so if we pick any 2 numbers, we can then visualize it in a graph. And so let's say the orange shows up in the top right corner. Now let's repeat this process. So we'll start with banana. We'll send it through an embedding model. It'll create a mathematical representation, which gets stored in our vector database. And what you'll see is that if we pick those same 2 numbers, they show up very close to orange. Because we know both of these are fruits, an embedding model is able to capture that relationship, and so they show up very close to each other. Now we'll do it again. This time the word is queen. We go through the same process, and we'll see that it actually shows up pretty far away. There is a big difference between the word queen and banana and orange, which are fruits. Similarly, we do it again with king, and king will show up very close to queen. So you can see that these embedding models are capturing some information about this word, some context about this word, and that context then can be stored and visualized through a vector database. And we'll do this again with all of our domain knowledge, and it'll be spread out in our vector database. Okay, now let's say you're creating an application where a user provides a word and you're finding other similar words, right? So the user comes and provides us with the word mango. Right? And the output of our program should be, what are words similar to mango? So as we can assume, we are going to send it through our embedding model. It's going to create some embeddings, and this time now we're going to do a lookup based on those embeddings in our vector database. And what we're going to see is the mango shows up right there, close to orange and banana. And we can use something like cosine similarity, which will help us figure out how far our new embedding is from all the embeddings in our vector database. And then we can do something called k nearest neighbor, which is basically who are closest to this value. So in our case, let's say the k value is 2, right? So we want the 2 closest neighbors. And so we'll see that it actually finds that banana and orange are the closest in our vector space. And now we know what is the closest to our input, what is the most relevant context. And so right now I've been talking only about words, but this entire concept can be applied to documents, to schemas, to types, to sentences. And so what we could technically do is take a GraphQL schema, build small chunks of that, store it into the vector database, and then when a user query comes, find what is the relevant context. So as in this example, the user's request is find the user's bank account for billing, and then we can find similar what are the correct contexts for that user query. I'll now pass it on to Siva, who will really walk us a little more into how all of this works.
Yep. Thank you, Rachit. So Rachit gave an insightful overview on how we can generate embeddings for text documents using embedding models. He also explained how we can use semantic search in a vector store to find out relevant document chunks with a natural language query. Additionally, he illustrated the concept of retrieval augmented generation, using which we can send some data in the context to the LLM to ground the answer on. So in the upcoming slides, we will see how we have implemented RAG at Intuit for the query generation and GraphQL discovery use cases. So we currently have, we are using generative AI for these two use cases, field discovery and query generation. Field discovery is for a user to identify some attributes of field within a GraphQL schema. Let's say, for instance, a user wants to find out the trial start date of a product for a particular user. He can ask a natural language question like, what are the attributes I should use if I want to find out user's trial start date to a product? Similarly, developers can use query generation tool to formulate a GraphQL query and embed that in the code. Let's say a front-end developer wants to display the trial start date of a product in a user's profile page. He can ask a natural language question like, need a GraphQL query that will retrieve a user's trial start date to a product. So this query generation tool would generate a GraphQL query, which can be embedded into the code to retrieve the relevant information using GraphQL APIs. So in this slide, we will see how the end-to-end query generation and field discovery works with RAG approach. So like Rachit explained, we initially have all the schema field embeddings ingested into the vector database using the data ingestion pipeline, and an index is created. When a user asks a natural language question, we would do a semantic search with a top K value. We will get back the results. And then we would do re-ranking on the results using some heuristic and historic data, like let's say number of times a particular field was used in GraphQL queries for the past 30 days. Once we have a set of fields retrieved, we would build a minimal schema only using those fields and send that schema in the context to the LLM for it to generate a query or discover the fields. So this minimal schema that we generate would be a valid schema. It would be parsable and executable. And this approach of building a minimal schema helps us with a few aspects. Like one is that it reduces the inference time because we are shrinking the schema. And also it controls the hallucination. We are only sending a certain amount of data to LLM, so it would pick a field only within that minimized scope. So in terms of query generation, LLM would generate a query and it would be sent back to the user. And for field discovery, LLM would select what are the fields that are most relevant for the natural language question. And we would use the same order as it was in the re-ranking. So we will preserve the same order and send back the fields to the user. So we also have implemented evaluation pipeline for our generative AI applications. So implementing an evaluation pipeline is crucial for a generative AI application to continuously improve the accuracy. So and also this pipeline systematically accesses the key performance metrics for the application or a model, and it can be used to check, like whenever we do a code change or a model update, this can be used to see whether it caused any regressions. So we do have a human crafted golden set. It's a high quality benchmark golden set. And also we generated a synthetic data set using an LLM. So this LLM generated synthetic data set is to increase for further widen the evaluation scope. And the synthetic data set would have a better coverage for the fields in the schema. So when we run the evaluation pipeline, it would look for key performance metrics like the precision and recall. And this pipeline would help us improve the accuracy of our tooling over the time. So to measure the effectiveness of our GenAI tools, we are using the time the developers spend on identifying the attributes and generating the queries as the metric. So like Rachit mentioned, previously it used to take 2 to 3 weeks for developers to identify the different attributes across the large schema and then formulate a GraphQL query. With the implementation of GenAI tools, the same process can be done within 20 to 30 minutes. So here we saw a huge boost in the productivity of the GraphQL developers. So upon analyzing the results for these toolings, we found out that the quality of the schema is crucial for the accuracy of the outputs. So we built some tools around enhancing and elevating the quality of the GraphQL schemas. So we built a collision detection tool. What it does is it would scan the GraphQL schemas for semantic collision between fields and types. So we have a threshold set, and whichever the field or type that has more similarity metric than the threshold would be marked as collision. And then the developers would have to go update the field names to be more meaningful and update the descriptions to be more meaningful and make them distinct enough to avoid these collisions. We also worked on a schema enrichment tool which scans the GraphQL schema. And for the fields which are missing a description, it would automatically generate a description using LLM. And also we have a human in the loop review process for these LLM generated descriptions. Though the developer or the schema owners would review the generated descriptions and then merge them into the existing GraphQL schema. And also, like you see at the bottom of the slides, we have a pipeline to continuously measure the accuracy improvements via the enrichment. So we measure the precision recall metrics before and after the enrichment so that we would know how much impact the enrichment, each iteration of the enrichment has made. And also we enabled multi-turn conversations and disambiguations to improve the accuracy even further. So we allow LLM to ask questions to reduce the ambiguity and also increase the response precision. And on this pipeline, we also enabled query rewriting. So we use an LLM to rewrite the query. So it would transform the user question into a format which would be more relevant in the context of the knowledge base. So LLM enhances the question with more contextual understanding. And the rewritten question is used as the query in the RAG process to retrieve the results. And also, we additionally added ambiguity detection in the pipeline. So once the LLM generates the answer, it would evaluate if there is any ambiguity in the generated response. If it finds any ambiguity, it would ask a disambiguation question back to the user to clarify on the question. So this would help us when there is when the user's question is vague or too generic. The LLM would ask subsequent questions back to the user to narrow down the scope or to minimize the scope to avoid the ambiguity. Yep. Thank you, everyone, for attending our talk today, and we are open for questions. Yep. So like Rachit explained earlier, we are currently creating each field as a separate chunks and ingesting that into the vector database.
So essentially the schema coordinate is a chunk.
Yep. Each field in the schema is treated as a separate chunk.
What is the base model you're using?
Yep. So currently we are using GPT-4o as the model.
How do we keep the relationship between the fields? Yeah. So it goes back to how we store the embeddings. So our embeddings, if you think of GraphQL as a graph, there is a clear relationship from where it starts to the root node, and so we capture that relationship in a format like a dot separated format, and that enables us to know exactly how to go from a root node all the way down to the base node, and that also then allows us to know what are other nodes that might be similar to that, which share kind of the parent structure. Right. So I think if we go back and look at our pipeline, the important part here to look at is the minimum schema portion of it, right? So that is a dynamically generated schema for every request. So instead of using the entire schema that we have, because that schema is like 200,000 tokens, we generate a minimum schema, which is dynamically generated about 8,000 tokens large. That schema is basically a GraphQL schema, and that is provided as the context to your model. And so what we found is that if you think of these large language models, they're trained on internet data. And there is a lot of information on the internet on GraphQL. And so these models inherently have some kind of understanding of GraphQL, because at the end of the day, it is a structured data, and they have an inherent understanding of the relationship between this data. And so that's how it's able to easily derive, by providing a schema, how one thing might be associated with another thing. So I think you're talking about this portion of it? Yes. Okay.
Yep, so we do have tools available for schema augmentation. So we currently have a tool that enriches the schema description. So like the collision detection would help us find the fields that has similar semantic meaning or duplicate fields. And then we would use the enrichment tool to generate a new description for those fields. Yeah, even that scenario, even if the types belongs to two different subgraphs, they would be marked as collisions. And the developers would have to go at more meaningful descriptions, or they have to use the same type across both the subgraphs.
Yeah, so we don't use any LLMs for the dynamic generation. That is done deterministically through an algorithm that we have. So that basically ensures that whatever schema we create is a valid schema. There are no hallucinations, and it is valid not only from an executable perspective, but it's also valid from like the Intuit domain perspective. Exactly. The LLM could hallucinate, LLM could choose wrong things. So we want to avoid that portion of it. And so it's all done that portion is done deterministically. So I guess the way to think about a minimum word is that, like I said, Intuit has a really huge schema, right? And that schema could have, let's say, things about different parts of our business, right? So we've got QuickBooks, we've got TurboTax, we've got Mint, Credit Karma, right? So it could have, the same graph could have information from each one of them. When the user query comes, we can use the context of the user query to identify what domain they're talking about, or what are the correct attributes they're talking about. And then we can pick only those attributes and avoid all the other attributes, and then create a schema that has only those attributes, and make sure that schema is valid. And by valid, I mean it's from the correct root node to the correct, correct root node to the correct leaf node. And that way we have a much smaller schema, which doesn't have all the other unnecessary stuff that is not needed for this user query.
No, so like we have the top K value configurable. So let's say if you use top K as 30, it would retrieve the top 30 attributes and build a minimal schema using those attributes. So if you want to increase, you can increase that as well.
Yeah, like similar to the previous question, our embeddings are capturing those relationships in the schema. So as Siva said, by configuring our top 30, we can retrieve back different number of attributes, and all of those attributes have inherently stored the relationship within themselves. And so we can use the relationships to rebuild a new schema.
Yep, so the custom tool that Rachit mentioned, what it does is once we have all the fields added, it would check if any of the enums types are included. In that case, it would add all those enum and scalar types to the minimal schema so that it would be a valid schema. We would extract that and add it here. Yep. Yep, so like I explained, we do have a human-crafted golden set and also a synthetic data set. So every time we make some changes, we would run this evaluation pipeline. It would give us an overview of the precision and recall metrics.
So it really depends on the requests coming in and how much we need to find. So depending on the request size, the response time can be anywhere from a couple of seconds to maybe 10 to 12 seconds at worst. It really depends on how much information the user is requesting for. The more information they request, the more we look up. The more we look up, the larger context is providing to the LLM. And as the context increases, the more LLM has to process, right? And so that also touches back onto why we need this process. If we didn't have this process and we just took our raw schema, and let's say you have some new LLMs like Gemini, which have like 1 million context window, right? So let's say we took that 1 million context window and threw our entire schema. Our schema is still really large at that point, and so the processing time would be even much larger. And so that is another reason why we need such a pipeline that selects the most important information and provides only that information to the LLM. That results in a lower latency, and it also increases our precision, because what we've noticed is that although these LLM providers are promising huge context windows, 100K, 200K, a million, most of them are tapping out their performance at like 8K. As you go above 8K, you'll see a huge drop in your performance. And so that's another reason why we need this entire process.
No, we do have, we are using AWS OpenSearch as the vector database, and also the application is deployed in AWS, and we are using LangChain for the application.
And then the other thing I'll add is y'all can go out and look up this Intuit GenOS. If you just Google that, we've put out articles on that. And basically, Intuit has taken a very strategic approach with LLMs, where we've created what we call an operating system that enables us as developers to interact with different LLMs by just changing a label. And then internally, the operating system is able to figure out whether it needs to talk to Azure, whether it needs to talk to GCP, whether it needs to talk to Amazon. All of that is handled for us. And so our infrastructure is kind of spread out across multiple clouds today. So the re-ranking is done so that we can, so when we do a retrieval from the database, it's using only semantic information, right? And it is possible that although something might be semantically correct, it might not be the most useful piece of data, because maybe it's not used as much in production, or it's not providing the correct information, all of these different things. It might not even be the correct time of the year, right? It's not tax season, so the chances of someone needing that attribute might be low. There might be all of these different reasons. And so what we can do is we can bring all of these heuristics from different parts of our company and figure out that, hey, in this list of attributes, what is most likely attribute for the current request, given the current context, given the current time of year, and all of this information we can use. And then I think your next question was about why we don't do knowledge graphs. It's not that we don't do knowledge graphs. We are looking into that, and we are figuring out how knowledge graphs can work. We've just found till now that we've got really good performance, latency, and all of that with this approach. With knowledge graphs, there are different ways they can be created. One is using LLMs, but as you said, we have a really huge schema, and so you take that schema and try to create a knowledge graph. It can become not only computationally expensive, but also like just dollar expensive to do that. But we aren't saying that's not possible. We aren't saying that don't do that. We ourselves are looking into all of these approaches and trying to figure out if there are better approaches out there. But we've got really good results with this approach today. Yeah, so I think that goes into the user experience. How do we expose all of this experience to our developers? And so what we've done is at Intuit, we have a GraphQL Explorer. It just uses GraphQL. And we've just built functionality on top of that enables users to ask a question and generate a query, and that query gets automatically populated in the GraphQL window. And so then all they have to do is click an execute button, and they can see what the response might be like, right? And so they can do, so that enables the developers themselves to go through a really quick cycle where they send a message, generate something, execute, see what the executed data looks like. If anything looks bad, go back to the LLM, and they can go through this process much faster. And that's really what brings, as we said it during our metrics portion of it, from 2 to 3 weeks to 20 minutes, because now it's all on the developer on how fast they can go through this cycle. They aren't dependent on having to reach out to people, getting information, scheduling meetings, reading documentation. All of that is removed from the process now. Awesome. Any last questions? Perfect. Thanks a lot, everyone. Appreciate your time.
Thank you, everyone.